All right, welcome back. So sound check. So I'm a little sick, so got a little bit of sick voice, deeper voice than normal. That should be fine. So let's continue learning about machine learning mathematics. You can see I'm pretty inconsistent in this series. So learning math, I think the best advice is to just do a little bit every day. The more consistent you are, the better you get. So it doesn't have to be that every day you're making a big breakthrough, but if you let 9 days go by and then come back to it, you're just not going to remember what you did the day before. So I feel like with learning any really high levels challenging skill, you want to be spending about 2 hours a day on it if you want to rise to the very top. Um, at least. If you can spend more like 3 or 4, then it's more guaranteed that you'll be to the top. Beyond that, you're kind of putting yourself at risk of injury, and you're likely wasting a lot of time. So, I would say, from my own experience practicing classical music, the people that were really successful were just rock steady doing 2 hours every day, and then on top of that, they came from musical families that had all the best teachers, and they did everything they were expected, you know, above and beyond what they were expected. So that's really the key. If you want to be a professional, and honestly, I would say that's not even the key to being one of the best in the world. That's the key to just being a competent professional. Yeah, it's kind of sad when you think about it, because it's just hard to establish those habits, especially if you don't have like a family that instilled them in you when you were younger, or you just never quite connected the way you needed to with the right kinds of teachers, or like mentors. It's really hard to kind of dig yourself up from that deficit you have as compared to the people who have done the right things. But that's why the people who are at the top are so deserving of respect, because they did the things that other people tried to do and failed. So that's just my little rant for why I've been away for so long, and what effect that'll have. So that means that for this topic, I likely won't be an expert. All right, so let's continue reading this. Oops, and I accidentally highlighted that, so I'm going to delete that highlight. All right, and now we have figure 2.2, a mind map of the concepts introduced in this chapter, along with where they are used in other parts of the book. So this chapter is which chapter is this? I think it's chapter 2. So it should be about vectors, and I think I remember reading this before. So let's continue. So this chapter is mostly based on the lecture notes and books by Dram and Wheel. By these, so here's other resources. Other excellent resources are Gilbert Strang's Linear Algebra course at MIT, and the Linear Algebra series by 3 Blue 1 Brown. Linear algebra plays an important role in machine learning and general mathematics. The concepts introduced in this chapter are further expanded to include the idea of geometry in Chapter 3. In Chapter 5, we will discuss vector calculus, where a principled knowledge of matrix operations is essential. In Chapter 10, we will use projections, to be introduced in Section 3.8, for dimensionality reduction with principal component analysis, PCA. Sorry, and I am sick. In Chapter 9, we will discuss linear regression, where linear algebra plays a central role for solving least squares algorithms. Alright, this is section 2.9, so I think we're in chapter 2 here. Systems of linear equations. Systems of linear equations play a central part of linear algebra. Many problems can be formulated as systems of linear equations, and linear algebra gives us the tools for solving them. Example 2.1. A company produces products n1 all the way on to n of n, for which resources r1 onto r of m are required. To reduce a unit of product, nj aij units of resource ri are needed, where I equals 1, ellipses m, and j equals 1 through n. The objective is to find an optimal production plan, for example, a plan how many units x of product n should be produced if a total of b I units of resource ri are available, and ideally no resources are left over. If we produce x1 through xn units of corresponding products, we need a total of this many units of resource ri. An optimal production plan therefore has to satisfy the following system of equations, where so let's get this unpacked by ChatGPT. This is a doozy here. And it's gonna be hard to do that. So we're gonna say, and we are going to include the footnote in here because that might help ChatGPT to have a better understanding of how to deliver the answer. Okay, so we got one screenshot there. We've got another screenshot here. So we're going to say unpack example 2.1 into plain English. And this is example 2.1, yep. So unpack example 2.1 into plain English so that it can be understood without knowing what the symbols mean. When you are done, provide a legend that shows each symbol and equation and how it was unpacked into plain English. And my keyboard doesn't work anymore, so I'll use my other keyboard. So when you are done, provide a legend that shows each symbol and equation and how it was unpacked into plain English. Alright, so hopefully this will help, assuming it's not hallucinating or making things up. And it gets it right. So let's read the plain English version of example 2.1. A company makes several different products. To make each product, they need a certain amount of resources. Think of resources like raw materials or time. And each product requires a different amount of these resources. The company wants to figure out the best way to plan their production. Specifically, they want to decide how many units of each project they should make so that, number one, they use up all the resources they have available without wasting any. And number two, they meet a specific amount of resource usage for each type of resource they have. For instance, if they have 100 units of wood, they want to make products in a way that uses exactly 100 units of wood, and that sounds useful. Similarly, for every other resource they have, like metal or labor. To solve this problem, they create a plan for how many units of each project they should make. This plan must ensure that the total resources used for all products exactly match the available resources. So there you go. Couldn't be easier to understand, assuming it's right. But let's see how they unpacked each symbol into plain English. So here's what each part means in plain English. So we have this here means the different products that the company makes. Yeah, so we can see. Yeah, so this is each of the products, and then this is the different resource. So I completely had this. I completely didn't understand that this stood for products. Assuming it does, but it's sometimes you can't really trust ChatGPT, but okay. And then this is the different resources needed to make the product. So we can see we've got a different letter, N and R. So N and R, yep. The company produces products. So yeah, we see very clearly N stands for products, for which resources R. So we're not using a P here because that would be too easy. Alright, so then we've got this symbol here. That one was a doozy. Kind of looks like Arabic. The amount of resource I, R, needed to make 1 unit of product NJ. For example, if Aij, subscript I, subscript J equals 3, this means making 1 unit of product NJ requires 3 units of resource RI. Oh, okay, that's brilliant. I like that. Next one is instead of an A, we've got an X here, and instead of IJ for the subscript, we've just got the J. So this is the number of units of product represented by capital N, subscript J, the company decides to produce. For example, if I subscript, and it's an italicized J, which probably matters, equals 5, the company plans to make 5 units of product capital N subscript J. B subscript I, and it's the lowercase b, the total amount of resource capital R subscript I the company has available. So for example, if B subscript I equals 50, the company has 50 units of resource RI to use. Alright, so here's the equations in plain English. So equation 2.2, that should be, yeah, so we can see the equations are numbered here very usefully. So here's the first equation. Let's see what this means. So the equation says, for this type of resource, the total amount used must be calculated by summing up how much of that resource each product uses. For example, if wood is resource R1 and the company makes multiple products, this equation sums up all the wood used for every product. Okay, so let's think about that more deeply here. So, all the use. Okay, interesting. All right, now we have equation 2.3. This is a system of equations that ensures, and let's look at the equation first. All right, so here we go. Yeah, so it's a system of equations. I think that's what this means. Yep, so this is a system of equations that ensures the company uses exactly the amount of each resource they have. It says for each resource, capital R subscript I, the total amount used must match the total amount available. So there you go. You know, how useful, like for people who are, you know, I'm sure a lot of people have heard this studying math. Oh, what good is the math? What does this mean? Who cares if A subscript 11 times X subscript 1 plus ellipses plus, you know, it's like, well, you got to unpack it, right? And when you unpack it and you truly understands what these means, of course this is useful, right? It's about using your resources effectively and not running out of them, right? So the people who say, oh, what good is math? What do I need this in my life? I'm just gonna, you know, I don't need math. It's just abstract. There's no concrete thing. You gotta understand it better, and you gotta unpack it into plain English, because we can obviously understand that it's important for someone to use up all the resources you have without wasting any, and it's important to therefore meet a specific amount of resource usage for each type of resource they have. So obviously, if you're building a bunch of chairs, you need to know how much wood you have, and you need to know how much wood each chair needs to be built. So it's people who say, what good is math? What, you know, what's the actual practicalness of it? Why am I learning it when I don't need to know it? Well, there you go. It's yeah. You're basically, when you're saying that, just saying like, I don't matter as a person, and I don't need to do things accurately or efficiently or in a way that matters and makes sense. So stop saying that, have better self-esteem, and learn math. All right, now let's move on to equation 2.3. Is the general form of a system of linear equations. And so, okay, we'll get that unpacked. Are the unknowns of this system every n dash tuple? There we go. And this means that is a part of the matrix, I think. I don't know. We'll get this unpacked. That satisfies 2.3 is a solution of the linear equation. So this is system of linear equations. This is what a solution is. Okay. All right. So moving on to example 2.2. Okay, let's have it do the same for example 2.2. And it looks like example 2.2 extends down here. So let's do that same thing. We'll get 2 screenshots, one for each page, and ask ChatGPT to do the exact same thing. Okay, and then we're going to say, great, now do the same thing for example 2.3. Oh, and we can see it actually failed to do the same thing. Sorry, it looks like you failed to do the same thing. I will be more specific in my next prompt. Let me know when you are ready for my next prompt. Okay. So now we'll take the exact thing here. We're going to say pack example 2.2. Oh, and I made a mistake because I told it 2.3 instead of 2.2, so it's majorly me to blame, but if it were smarter and more of a advanced AI, it would probably say, oh, did you mean 2.2? That would be nice if it could do that, but it's not sophisticated enough to do that yet. Alright, so this should be better. Okay, so now it did it properly. Perfect. Alright, and with that, we'll take a break. Alright, I am back. So now we've got this nice, unpacked, plain English explanation of example 2.2. Hopefully I'll be able to understand it better. So we've got it split into cases. Well, you know what? We don't have it split into cases. We have, yeah. So now we're going to read about the equations of 2.4, which we can see here. We are presented with three statements, equations, about how three quantities, call them x1, x2, and x3, relate to each other. These statements should all hold true together if there's a solution. However, when we add the first two statements, we find a result that directly conflicts with the third statement. So let's see if there's anything in the symbols that might... yeah, so it has no solution. Adding the first two yields which contradicts the third. Okay, perfect. Adding the first two equations gives us one total for a certain resource, but the third equation states a different total. So let's see if we can see that happening. So if we add these two equations, we get 5. Yeah, so adding the first two equations means it will equal 5. But if you add the left-hand side, all right, I'm very confused by that. That's beyond me. Since it's impossible for both to be true at the same time, there's no solution. This system is inconsistent. Alright, so I definitely want to drill into that further because I don't understand it, but let's try to get through all this first. Alright, so the second case, equations 2.5. Here we are given three different statements about the same quantities. This time, number 1, the first statement tells us that the sum of three quantities equals 3. Combining the first and third statements lets us find out the first quantity, x subscript 1 equals x, or sorry, equals 1, not x. Substituting this back, we can solve for the second and third quantities, finding that x subscript 2 equals 1 and x subscript 3 equals 1. So it's the same. How does that work? Is that a log? Is that logarithm? Or is that the quantity in the series? What? This time everything checks out. We have one and only one combination of values that satisfies all three statements. So there is a unique solution. The quantities are all equal to 1. Third case, equations 2.6. In this case, we start again with three statements, but this time, number 1, adding the first two statements gives the third statement exactly. They don't provide new information. Number 2, this means one of the statements is redundant and doesn't affect the solution. Number 3, instead of having a unique solution, we have some flexibility. We can pick a value for some quantity, say x subscript 3, and from that calculate the other two quantities. This leads to infinitely many solutions depending on what value we choose for x subscript 3. Legend, symbols and meaning. Okay, so x subscript 1 through 3, these are unknown values or variables we are trying to find out. So in some cases we found that those are equal to each other. And then the equations are different systems, also known as sets, of relationships among the unknown values or variables. Alright, and then equation 2.4 has no solution because combining two statements leads to a contradiction. Equation 2.5 has a unique solution where x equals 1 for each of those instances, for each of those unknown values that we are trying to find. And then equation 2.6 has infinitely many solutions depending on the value you choose for one of the variables. So it's important that those are three things that can happen. The first thing that can happen is you end up with no solution. The second thing that can happen is you end up with a perfect, unique solution that's probably the best outcome. Well, it depends on what you're doing, probably. And then the third thing that can happen is infinitely many solutions, depending on the value you choose. Okay, so let's get a little bit of a chat going about that. Okay, so this makes sense to me now, I think. Basically, this describes three things that can happen. The first thing that can happen is you get no solution. The second thing that can happen is that you get a perfect, unique, one answer, clean solution. And then the third thing that can happen is you get infinitely many solutions. So give me like a real world example of this, like you were talking about earlier, where like a factory was making products, like put this in like real world terms, as if I were going to like use these equations to do something in the real world, and describe the three outcomes that I could have in a real world way. You know what I mean? Yeah, so let's so we're gonna have so I own a factory and I'm producing tables, chairs, and desks. Each of these products requires three types of resources: wood, metal, and labor hours, people to build them, or machines going on into the future. The goal is to figure out how many tables, chairs, and desks the factory can produce given the available resources. Here's how the three cases from the system of equations play out in this scenario. So case one, no solution. So we have an inconsistent system. If we imagine that the factory has 100 units of wood, whatever that means, so we can say like 2x4s or whatever, and then you can, the labor hours are cutting that down to size, drilling in the screws, so 50 units of metal, so you could think of that as like the screws to screw them together, and then 200 labor hours. So the equations representing the resource usage might look like this. So tables plus chairs plus desks equals, we need 100 units of wood, okay, and then two tables, so building tables at twice the rate of chairs, plus 3 times desks, so building for every chair we build two tables and 3 desks. That would equal 50 units of metal. And then for every chair we build, and then for every 4 desks we build, we only build half the amount of tables, and then a third, and then 3/4 the amount of chairs. And that would be 70 labor hours. Now, when the factory tries to solve this problem, they find out that the first two equations together imply a total labor requirement of 90 hours. But the third equation claims they only need 70 labor hours. These numbers contradict each other. So there you go. You can see how important this is to do these calculations if you do have a factory or something like this, because the factory's goals are unrealistic or based on incorrect data. You need more labor hours. You have to hire more people. You miscalculated how many, how much this is going to cost in terms of labor hours. Maybe they underestimated labor needs or underestimated or overestimated available wood, but they cannot meet their production goals with the resources they have. So that could be it too. Is okay, maybe tables, chairs, and desks don't need 100 units of wood. If that's the case, then it would require less labor hours. So something is off, right? Because the first two equations together would imply a so okay, and we can see so the first two equations of together, so we can see we would need 200 labor hours because we used so we have 100 units of wood, we have 50 units of metal, so 100 units of wood. In order to use up each of our 100 units of wood, we would only be able to create one table, one chair, and one desk. So we'd be able to create 3 items. But if we use each of our 50 units of metal, now we are able to create 2 tables, 1 chair, and 3 desks. So okay, so now that we have this number, now that we have these equations, we can manipulate them. Oh man, this is confusing. I think there's a mistake here. Oh, but that's the point, right? Is like there is a mistake somewhere, right? So like there's no solution because something was messed up. Either the adding of the equation didn't go right, but the like accurate way it's supposed to go wrong is that these units aren't corrected, and you calculated how many labors it would take, how much metal you needed, how much wood you needed, etc. And that could work in your favor or out of your favor. If you estimated that you needed too much wood, hey, good outcome. You only need half the wood you thought, and you save a lot of money. So alright, so case number 2 is the unique solution, the perfect fit. So this time, let's say the factory has 150 units of wood, 75 units of metal, 300 labor hours. These equations now might look like this. Okay, so this is confusing here to me. I don't understand why there's one table here, because it should be... Yeah, I just don't get this. So when the factory solves this system, they find exactly one set of values for the number of tables, chairs, and desks they can make. So they can make 20 tables, 50 chairs, and 30 desks. Real world interpretation. The factory has found a perfect production plan. They will use up all their resources without any waste or shortage. And there's only one way to achieve this plan. So that's probably what you're aiming for in most situations. And let's try. So we've got 20 tables, 50 chairs, and 30 desks. So 20 plus 30 is 50. So 50 plus 50. What? Okay, so this is one thing ChatGPT is notorious for, is getting math wrong, getting specific numbers wrong. So something is missing from my prompt. It's probably better to use the O1 with advanced reasoning. But but O1, my usage limit would be pretty low. I think I can't use screenshots in O1. Another option would be switching to Claude. I've heard good things about Claude. And then, from what I understand, there's been a lot of brain drain at OpenAI, and that hasn't been the case so much with Claude. Or, I think, is Anthropic the same as Claude? I feel like Anthropic is the company. Yeah, Anthropic is the company and Claude is the product. So, Anthropic hasn't had the same kind of turnover as OpenAI. So, you know, there might be a point where ChatGPT isn't the number one best on the block. All right, so rule or interpretation. There we go. We read that already. So then case 3 is infinitely many solutions, flexible plans. So now let's say the factory still has that amount, but the resource usage equations are that. And then the third equation turns out to be redundant. It's just a combination of the first two. So here solving the equations reveals that as long as the factory balances tables, chairs, and desks according to the first two equations, they can produce many different combinations of these products. For example, they can create all these different options. So rule or interpretation, the factory has flexibility in production. They can meet their resource constraints in multiple ways depending on demand or preferences. If customers suddenly want more desks, the factory can adjust without running into resource problems. So, summary of real-world outcomes. So we can have no solution. Production is impossible with the given resources. Something needs to change. More resources must be acquired, or production goals adjusted. We can have a unique solution. There's only one way to meet the resource constraints exactly. This is a tightly optimized production plan with no flexibility. So you'd think that would be the best, because then you have a clear direction for what to do. But I would say the best real-world outcome is number 3. Infinitely many solutions. There are multiple valid ways to produce products while staying within resource limits, offering flexibility to adjust to changing needs. Perfect. This kind of analysis is crucial in supply chain management, operations planning, and resource allocation to ensure efficient uses of material and labor. All right, perfect. This is really helpful to me. Thank you. So now you say the kinds of things that this analysis is crucial for. Is it also crucial for artificial intelligence and machine learning? Tell me briefly how it is crucial for that, if that is the case. If it is not, then tell me that it is not crucial for it. Yeah, so it is crucial for it. Otherwise, it wouldn't be in the book. Linear models and optimization. Okay, so finding those weights. Neural networks training. Gradient descent, it helps with that. Resource allocation in AI systems. So that's definitely an intuitive one. So how much power, memory, or energy, it has to optimize that. And then data fitting and over/undetermined systems. Real world AI applications. So, yep, absolutely fundamental. All right, so moving on. And let me read this through. So the system of linear equations has no solution, so remember that. Adding the two equations. Okay, so we add these first two. So here we can kind of do a get back to get out of that world of AI where it makes mathematical errors and it needs a more sophisticated model optimized for reasoning in order to get things right. So if we go back to the textbook, we should see the numbers start to make a lot more sense. So we can see the first system of linear equations has no solution, and we can see that adding the first two equation creates this. So let's do that. So if we add, so remember how multiplication works. So if we have if I have 3 apples, you have 3 apples, and then somebody else has 2 apples. That's, you know, that's a combination of addition and subtraction, addition and multiplication, because you can say that my instance of 3 apples and your instance of 3 apples combined are 2 instances of 3 apples. So you can multiply our instance of 3 apples by 2, but then adding 2 apples to the mix, there does not exist another instance of 3 apples, so we cannot use multiplication there. We have to add the remaining 2 to the result. Now, if a third person had 3 apples, a fourth, a fifth, or a sixth, now we know that we have multiple instances of the same quantity, 3, so we can multiply them, and we don't need to add anymore. But you could also add. It's the same thing. So we could just count up how many apples people have. But since we know multiple people have the same instance of apples, we can just multiply their instances of apples by the number of instances of that quantity of apples that occurs. That we have. So there we go. So that's what we got here. X subscript 1 plus X subscript 1. We have 2 instances of the same quantity there, X subscript 1, so we can multiply it. So 2 times X subscript 1. Now we can see that we have an instance of for example, let's say that you owe me an apple. Or we have an instance of, let's think of it on a number line. So we have one quantity moving up on the number line. Let's start, we start the number line at 0, and we move it one quantity up, and then we move it the same quantity down, then we're back at 0. We didn't move on the number line at all. So even if we start the number line at 5, we move it the same quantity up with this addition here, and the same quantity down, we didn't move on the number line at all. So you can think of it that way. There's no movement on the number line here. So that's our second term. A third term, so we have another instance of the same quantity, so we can multiply it. So 3, there we go. So so now we can see these numbers do actually make sense, unlike the ChatGPT numbers, because ChatGPT is notorious for getting math wrong. It doesn't really have a reliable system to sort of thinking. As of yet, it does in a very primitive state. That will change. That will change very quick, and that will be something that really shocks people. Well, I mean, people are skeptical that will change, but I think it will. I think it will. It might take a while. It might take until like 2027, 2030, but I mean, that's going to change the world once it really gets reliable at that. But in the meantime, we can just go to the textbook, and we know that we you know, 99% of the time, if it's a published reputable textbook and it's received proper editing, these equations are going to make sense, and there aren't going to be mistakes in them. So we verified that there weren't any mistakes in it, but we can see with what these equal, you know, so it's not, it doesn't make any sense. So if we add, we can see it right here already. We don't even have to worry about the complicated math on the left side. 3 plus 2 equals 5, not 1. So we don't even have to concern ourselves with what's on this side. We can see very clearly that there's a, you know, this does not equal these two quantities added up. It equals 1 rather than 5. Okay, and then here's one where it does, yeah. This doesn't equal 5 either. Okay, maybe I'm not understanding that correct. So let's look at the system of linear equations here from the first and third. It follows the, okay. I guess I don't understand this. All right, let's try plugging 1 into this equation. So 1 plus 1 plus 1 equals 3. 1 minus 1 equals 0. 1 times 2 is 2. But now we can see 2 times 1 is 2, plus 3 times 1 would be 5, but here it equals 1. So that's not the case here, even though this equals 3 and this equals 2, and we add the equations. So this is just, I guess this is just a shorthand that you can do, where well, let's talk to ChatGPT about this. Okay, so I've got a point of confusion I'm hoping you can help me with. So in example 2.2, we've got equation 2.4 and we've got equation 2.5. Now a point is made in equation 2.4. We're adding the first two equations that are a part of 2.4 contradicts the third equation, and I can see that for myself very clearly, and it's really easy to see that if you look at the right hand side of the equation, because 3 plus 2 does not equal 1, it equals 5. So that is easy and plain for me to see. But where it gets confusing is in the equation, the set of equations 2.5. If you look at the right hand side of the equal sign in 2.5, 3 plus 2 does not equal 5 here as well. It equals 2. So I guess I don't understand how you can add the equations together and get a valid answer without the other side of the equation adding up to a correct number. Please explain in plain English. Alright, so the key idea is when you add two equations, you're combining their entire left-hand sides and their right-hand sides. Both sides of the equation must remain equal after you combine them. Okay, so system 2.5 recap. You're given these three equations. Now this is 2.5, remember? So this is the one with one possible solution. Let's focus on adding equations 1 and 2. So, yep, so there we go. And then the right-hand side will be 5. So, there we go. Oh, okay. So this equation is a valid new equation that represents a combination of the first two equations. It does not have to match equation 3 because we are simply combining the information from equations 1 and 2, not equation 3. Okay, so we can, let's go back to the book, and we can see when we add these up, we get 2x. Then we, what? Oh, I see. So we have a different third equation now. So when we add these up, we get, and it should say that here. Yeah, there we go. So we get 2x. This cancels out again, and now we get 3x. So okay. So right. So it got confusing here. Okay, let me talk to the ChatGPT. Okay, this is why it got confusing. It got confusing to me because in 2.4, it was unclear to me that the third equation was just simply given as an example of an equation where it illustrates the point that systems of linear equations can have no solution. And this was confusing to me because the third equation appears to equal adding up the first two equations, except for the other side of the equal sign. But really, what this is intended to illustrate is that this particular third equation results in a system of linear equations with no solution. So it's just coincidental, really, that the left-hand side of the equation equals adding up the left-hand sides of the other two equations. Understanding this, I can look at 2.5 more clearly, because I can see now that the third equation given is a completely different equation that is not the result of adding the first and second equations. And in fact, the result of adding the first and second equations does equal 5. So where I got confused was I thought the third equation was the result of adding the first two, but really the third equation is a completely unique equation given to illustrate the point that systems of linear equations can have three outcomes: an outcome with no solution, an outcome with an exact solution, and an outcome with infinite solutions. Exactly, I nailed it. Yay! Man, it's so easy to learn math nowadays with ChatGPT. Like, my God. Like, this is so easy. Because this is the kind of thing where, like, I would never have figured this out, like, in a classroom with a teacher. Like, the teacher doesn't know. Like, you know, it's like everyone would be making the same mistake in the class pretty much. You know, back in my day, the only way you got ahead in math is you were crafty enough to, like, cheat. Like all the best students in math just cheated. There was, like, one, like, really good student that, like, actually knew what they were doing because they were, like, from a mathematical family and grew up, like, doing math and stuff and, like, really liked doing math and was just, like, pretty naturally talented at it. But, like, everyone else, it's like nobody can explain this. And then I feel like a lot of people who are, like, really good at math are, like, they're just, like, doing it mechanistically. Like, they don't actually, like, understand, like, what's going on. They're just, like, really good at the like, manipulation of it. I don't know. I'm not one to speak on this. I don't have any major accomplishments in math. Alright, so there we go. So now it's more clear, and we'll read the response to reinforce that. So I nailed it exactly. So here's a quick recap to make everything crystal clear why the confusion happened. In 2.4, it might look like the third equation is just a result of adding the first two equations. However, the third equation is independent and not derived from the first two. It just happens to coincidentally equal the... And really, it doesn't equal it at all, because we know that the other side equals a different value. The purpose of this setup is, so it's not derived from the first two. The purpose of this setup is to show that sometimes, even though the first two equations might seem compatible, introducing a third equation could create a contradiction, leading to a system with no solution. In example 2.5, the third equation is also independent. However, it doesn't contradict the system. Instead, all three equations fit together neatly, resulting in a unique solution. So here's the key takeaways. No solution because the third equation contradicts the combined information from the first two, and that might have to do with it being the same as adding the two up, but with the result of that not equaling the same as adding the two up. And then the unique solution, because all three equations work together without contradiction. And then the other one, infinite unlinear solutions, because the third equation is redundant and there's flexibility in choosing values. So my understanding is spot on now, I will say so. Each system in these examples was carefully designed to illustrate one of three possible outcomes for systems of linear equations. The key is that the third equation in each case is a unique independent equation, not necessarily the result of adding the others, and actually in none of the three cases was it the exact result of adding the three others. Actually, that's not true. In this last one, it was the result of adding the three others, and that illustrates a equation with infinitely number of solutions. Oh wait, hold on a second. Okay, so I'm thinking about simplifying these. So this simplifies to 3 times x because we have. Oh, you know what? Actually, we don't know that these are the same quantities, I think. Okay, yeah, we don't know for a fact that x subscript 3 is the same quantity as x subscript 2. So you could definitely add these up because we know x subscript 1 is the same quantity because it's represented by the same symbol. Okay, but we can omit the third equation. Um, man, this is getting wacky. Alright, so tell me more about why we can omit the third equation from example 2.1, the equation labeled 2.6. In that third example there, that is labeled 2.6, it says that we can omit the third equation because it is redundant. And then it gives an example in 2.7. So tell me more about why that third equation that is a part of the set of equations in 2.6 is redundant, and then explain 2.7 in plain English. I'm kind of getting lost in that regard. Alright, so let's understand why 2.7 is redundant. So we've got the equations here, and it might get this stuff wrong. It gets that wrong pretty often. So it's redundant because you can derive it by adding the first two equations. So let's look back in the book because we don't know if I got that right. So we should be able to derive this third equation by adding the first two. You know what? We see that is the case. So now, oops, and I accidentally clicked on something that I didn't want to click on. And that complete. Oh, here we go. So, that took me to ChatGPT. I wanted to go here. There we go. So yeah, this is the exact same as adding the first two, and that means it's a redundant equation. So a simpler example, let's say we have two equations. The first one is 1 + 1 = 2. The second equation is 2 + 2 = 4. So the third equation, 3 + 3 = 6, tells us the same thing. It tells us that double one quantity equals double that quantity. So 1 + 1, we get 2. We get 2 instances of 1. 2 + 2, we get 4 because we get 2 instances of 2, and so on. We don't need to rewrite the equation again and again and again. We don't need all three of those equations. We can just use one equation to describe all three of those things. And the equation would be 2n would be 2n equals 2n, you know. Or like 2n equals n times n, you know. Or all right, so from that we get there. So let's keep reading the AI explanation. I think that really helps. So we can claim that it's redundant. Why? Because you can derive it by adding the first and second equations. We saw that. So so this isn't exactly so by adding them together, we get what was shown in the book. Hopefully that matches, but the AI can get that wrong. So this isn't exactly the third equation yet, but by dividing both sides by 2, okay, so now so key point, equation 3 doesn't add any new information because it's just a combination of equations 1 and 2. Since it can be derived from the others, it is considered redundant. There we go. So let's do the math in the book. So we can see that this is the same as this, because if we divide both sides by 2, we get 5/2 equals x subscript 1 plus 3x subscript 3. Okay. And we don't know that they're the same values, and they're different quantities, so we can't multiply them because we don't have multiple instances of the same quantity. We have multiple instances of different quantities, so we'll have to add them. Presumably different quantities. They could be the same. We don't know. Okay, so now that we have x1 plus and I can do this on. I wish I had a writing tool, kind of like the Khan Academy guy. That would be awesome. I don't have that. I do have a whiteboard, but I can't show the whiteboard as part of this channel. I would love to do that. That would make my day. But you know what? I bet you one of those things are not that expensive. And I do have you know what? I do have this tool. I have it right here, right now. So let's plug it in and use it. Heck yeah. No, I absolutely have this tool right here, right now. Alright, so let me turn the tool on. For anyone curious, it's a Samsung Galaxy Tab A. It's like the perfect tool for this. I actually bought it specifically for this reason. Yeah, and I love this. I love this thing. I've used it for many, many years. Look at that. It still powers on. At the time, it only cost me a few $100, and I've been using it for probably over 10 years. It's just, I could not have asked for a better tablet. For a better thing that satisfies my needs. Okay, so now I can go to a sharing tool, or I can figure out how to set it up so that it shares. All right, it's still powering up. I haven't powered this thing up in many years, so it might take a while. And I have to get it onto my Wi-Fi as well. That might take a while as well. Okay, but there we go. It didn't take that long. So now, let's get it on my Wi-Fi. And I have to remember my password. And I don't remember my password in the slightest. Okay. Man. I do not remember my password at all. Okay. Man, how do I get my... I'll have to pause it, but let me log into my router, and there should be an option to show what my password is. Or just, I can probably use, like an access code or something. Oh, shoot. Oh, man. Why do they have to make it so secure? Just locks me out from using it. So, so here we go. This should probably do it. So I'm gonna pause it and get my tablet on board. All right, welcome back. So I've got my tablet on my home network now. So next step would be to see how I can. I think S Note would be good. So now that I have ChatGPT, I can figure out how to use this. So so let's go right to I'm just kind of looking around on S Note now, but let's go right to ChatGPT. That's the best way I think I can figure out how to use this. Alright, so I have a old school Samsung Galaxy Tab A. I have S Note on it. So how can I set this up? Right now I have it connected to my home Wi-Fi. And what I would like to do is to draw on my tablet and have it show up on my other computers. So I used to do this with a browser tool called like Sketch or something. But it'd be great if I could do this just with what I have on the tablet already, such as S Note. Is this possible? Okay, so without relying, yep, so that's what I want. So what we could do is screen mirroring. So let's try that. So many support Smart View or screen mirroring. So to do that, I would have to swipe down from the top, look for Smart View or screen mirroring, and tap that. I don't see it so far. Still don't see it. Ah, Smart View. I see it. So view. There we go. So let's do that. So we're gonna do that. Then we're going to oh, so actually I don't have a okay, it looks like I don't have yeah, so I'm trying to connect to my neighbor's smart TV now. They'll probably get a notification if they're watching TV, but unfortunately I don't have yeah, okay, so we could use the Miracast or the Connect app. All right, so that's the way to do it. Could also use Samsung Flow. We could use okay, so let's try Miracast. This might work. I'll mute that. Huh. Projection? Is that a thing? Oh, it is. Okay. Okay, so that looks good. Optional features, and we can do add wireless display. So let me try that. Okay, optional features. So search that, add. Okay, so the wireless display looks good. So let's click that and go next, and then we'll add that feature. There we go. So we're adding a wireless display. Perfect. Okay, and so we've got a guide here. So there we go. Mirror Android to Windows 10. Okay, and I think once that is finished, I should be able to use that that Smart Connect that I have, and it should show up that this computer is an option. So it's gonna take a while. So I need a quick break. I'll be right back. All right, I'm back. So this is gonna take a while. So while this is going, let's continue with the reading here. Okay. So I can delete all of this. So yeah, let's read 2 to 7. So what does 2.7 mean in plain English? It represents the general solution for the system. Let's unpack it step by step. So this means that A is a free variable and can take on any real number. It introduces flexibility, so A can be anything. The solution is written as a triplet. So the system has infinitely many solutions depending on the value of A. Once you pick a value of 4x3 which is A, you can plug that into the formulas. So for example, if A equals 0, okay, so we plug that in. So this whole thing, I think, is A. Oh. Well, I'm still confused. In real-world terms, the flexibility could represent how the factory can make different combinations of products, chairs, desks, and tables, as long as they satisfy the constraint, the resource constraints. The third equation isn't necessarily, because the first two already fully describe all possible. The third equation isn't necessary because the first two already describe fully all possible valid production plans. So why is this useful? By identifying redundant equations, you can simplify your system and get the full set of solutions. It's like saying, I already know enough from two pieces of information. The third just repeats what I already know. So there we go. Alright, so moving on. Yeah, we can read this a little bit. So there we can met the third. So we'll define this as a free variable, such as any triplet is a solution of the system of linear equations. For example, we obtain a solution set that obtains infinitely many solutions. So figure 2.3, the solution space of a system of two linear equations with two variables can be geometrically interpreted as the intersection of two lines. Every linear equation represents a line. Okay, so this actually, believe it or not, for me makes it a lot easier, right? Because you can think of it more clearly. We've got so if we've got lines on a graph, there's three ways to write the lines. You can write the lines so that eventually they intersect, and they intersect in only one place because they're straight lines. They don't curve or anything like that. So we know that any way you write the lines, you can write it in a way that they intersect. We've also got another way we can write the lines. We can write the lines so that they're parallel, so that they never intersect. And then we've got a third way we can write the lines. We can write the lines exactly on top of each other so that it appears as though there's only one line, even though the lines are in this are separate. We could draw them in different colors, one in yellow, one in blue, and then we'd get a green line going that, and it'd be difficult to tell whether there were in fact two lines or not because they would completely overlap. So that makes it for me, that makes it really easy to understand what we're talking about. We're talking about straight lines on a graph that either intersect, that either are parallel, or that either are happen to be the exact same line. So in general, for a real valued system of linear equations, we obtain either no, exactly one, or infinitely many solutions. Linear regression, covered in chapter 9, solves a version of example 2.1 when we cannot solve the system of linear equations. Remark, geometric interpretation of systems and linear equations. Okay, so I don't know what remark stands for, but we do have, so that's not, remark is not an acronym. I don't know what this section is about. In a system of, so I guess it's just a remark on geometric interpretation of systems of linear equations. In a system of linear equations with two variables, each linear equation defines a line on the x subscript 1, x subscript 2 plane. So we can think of these as points on the graph. So here we have yeah, so they're labeled here. So we have 1 point here and 1 point there. So it's a line that intersects those 2 points. Since a solution to a system of linear equations must satisfy all equations simultaneously, the solution set is the intersection of these lines. The intersection set can be a line if the linear equations describe the same line, a point, or empty when the lines are parallel. Exactly, that's exactly what I said earlier. The illustration is given in figure 2.3 for the system. There we go. Where the solution space is the point. Similarly, yeah, and we can see where the point occurs. The point occurs at so this would be a 1, and this would be a 1/4. So they're not labeled, but we can tell what the labels are because of what these points are. Similarly, for 3 variables, each linear equation determines a plane in a 3-dimensional space. When we intersect these planes, for example, satisfy all linear equations at the same time, we can obtain a solution set that is a plane, a line, a point, or empty when the planes have no common intersection. Alright, I guess I don't understand what a plane means there, but we can get an explanation from ChatGPT. For a systematic approach to solving systems of linear equations, we will introduce a useful compact notation. We collect the coefficients a subscript I subscript j into vectors and collect the vectors into matrices. In other words, we write the system from 2.3 in the following form. Alright. In the following, we will have a close look at these matrices and define computation rules. We will return to solving linear equations in section 2.3. So that's it for that section. The next section is matrices. So there's a few things I would like to do before moving on. So we've got a wireless display added. So let's see if I have another option on my tablet to connect to a SmartView device. So we've got nearby screen mirroring and SmartCast devices will be shown here. But unfortunately I do not see one shown. So I guess I'll try opening that again. Okay, so I had to open that, and now that it's ready, aha, there we go. So I've got it popping up, and look at that. So now I've got a new tab here, just like any other application, like a browser, like this Kindle application, and there we go. Here's my screen. So we'll do a yeah. So it's not completely up to speed, but wow, this is really cool, actually. Cool. I was actually looking for this for a while, for how to do this. It's just in the age without ChatGPT, I couldn't figure it out. Okay, now I need my mouse back. My mouse disappeared on me. Alright, I don't know how to get my mouse back. What if I hit escape? Does that do it? Oh, it's okay. So now I'm sending. What if I hit a Control G? I remember doing that. Okay. Well, my mouse looks like it's I'm controlling my tablet with my keyboard now. Or my. It looks like I might be able to control my tablet with my mouse. Huh. This is interesting. Alt F4. Okay, well, Alt F4 still works, but I do need to figure this out. Okay, so protected. It says that protected content can't be viewed, so hopefully my content is not protected. Okay, now I do have my mouse here, but we can see when I moved it, it disappeared. Okay, that's how I changed the device. This is interesting. So it looks like I might have to actually pause the connection if I want my mouse back, which isn't ideal. Yeah, so if I pause sharing, hopefully I get my mouse back. No, my mouse disappears. Alright, well, this is a good one for ChatGPT. So we can resume sharing, but I don't have my mouse. Alright, so I will disconnect sharing, which I'm not able to do. There we go, I disconnected, so now I get my mouse back. So let's try a Control S. Let's see. So we've got the allowed devices here, so we'll click that. Okay, so now not only do I do have my mouse back, but unfortunately I can't exit that, so Alt F4 makes sense. So let's do, let's further that conversation before. Okay, so I'm close, but now I've got the connection formed and I can see my Android screen shared on my computer, but the problem is I lose access to my mouse when I do this, and if I figure out how to full screen the screen share, then there's no way for me to exit it without doing Alt F4 and closing the application. What I want to do is to seamlessly switch between showing my tablet screen and working on my computer. I want it to work like a browser where I can just like shrink it down when I don't want to show what's on my tablet. Okay, so I might have to use a different application. So screen copy. Let's just try a screen copy. I like this better. So, so the first thing we need to do is to get the app. So we got to read how to run for Windows. So the device has to meet the prerequisites. Okay, I'm not sure if that's the case. I might have an outdated version of Android. Okay, so then okay, so the first thing we gotta do is install it for 64-bit. Alright, so then we'll extract it. Okay, so now that it's extracted, I think we've got a bat file in there. Yep, we've got a bat file here. Alright. And then all we gotta do is type in the command. Oh, so then it started, could not find any device. Alright, so I think what might be happening is my version of Android. Configure and reconnect the device. Huh. Alright, so let's try this one. So we're gonna get the IP of my device, and then the port would be we'll try the default port 5555. Oops, didn't want to do that. Okay, so port's gonna be 5555. Okay, and then the IP I'll get from my router. So device list, this should be listed there. Yep, tab A is right there. So here's the IP. Oh, and we can see we've got a problem here in the pasting, but easy to fix. Oh, and we've got an unexpected additional argument. Oh, okay. So we do need that equal sign, I think. So that it's one argument. Alright, so no connection can be made because the target actively refused it. Let's try to connect it on another port, on port 80, because that port might not be refusing. 443 might not refuse on that port. Alright, so it's not set up to accept the connection. So maybe there's a way I can change that. So settings, connections, and then more connection settings. Alright, we'll try advanced features. Huh. Okay, and now I can see, I do see the version that I'm running, so that definitely could be a problem. So we can see prerequisite is we need auto forwarding, and we need Android version 11 or higher. I have Android version 7, so yeah, it was a good try, but I don't think it's gonna work, and I don't think my my tablet's old enough by now. It probably doesn't even have the ability to upgrade. So let's do the Smart Connect again, because the Smart View, because that was kind of working. There might be a way to get that to work. So we're gonna do wireless display. Okay, and then it should show up here. Yes, it is. So now it's connecting. So I like this. It's just the problem is there we go. So that's all I need to do is just hit Alt Tab. So I like this. This works. Alright, so I got it. Okay, so let's hide the notebook and shrink this down. Okay, and now I can do this. So there. Now I've got my. The problem is when I so we can shrink this down. Okay, make this bigger. There we go. This works. So now the issue is it's going to make my mouse disappear, but should be okay. All right, look at that. So we're in business now. Look at that. Perfect. Could this be any better? All right. So we're in business. Okay. So let's do it. So we've got I'll just write those down. So x1 plus x2 plus x3, and I want to emphasize I'm doing this with a old tablet. Like as I showed, I'm on Android version 7. The you know the latest version of Android is not Android 7. It's probably double that. I bought this tablet probably back like around like 2012, way more than 10 years ago, and it's just been sitting in a pile of junk, unused. So let this be a lesson to anyone out there. You can do a lot with a little. Like if you want to do what I'm doing now, forget about going to a fancy store or like buying the most expensive thing they have. Spend $50, spend $100, get an old ass thing, and you can easily do what I'm doing with it. Okay, so now let's take a look at why these two added up. Here, make this one redundant. So we'll add these up. So here we got 2 instances of okay, so 2x subscript to 1. Now if we add these up, we've got a 0 there. And then if we add these up, so this is where it gets tricky here, because we can't assume that we can't. So this is going to be x3 plus 2x3 okay, and then we know that the left hand side of that equation adds up to equaling 5. So how do we go? Oh, wait, we can add these up. Oh, you know what? It was the second one that I was confused about. Right. So what I was confused about is why is that third equation the same as these other two when it doesn't add up? But what I'll show is that it does add up. Okay, so now when we so this is where the confusion I was having is I thought that what this said was that this equation number one here, so I'll label that as equation number one, and this equation number two added up equal the equation number three. But this equation number three is just another equation given as part of our analysis. It's not meant to be the sum of equation 1 and 2 necessarily, unless it works out that way, and it is a redundant equation, which we see in example 2.6. But in example 2.5, that is not the case. Instead, we get a unique solution. So let's so this equation is unique. It is not a part of the other ones, and the stylus is very broken. It's just been laying around for forever. So okay, that's better. Piece of it fell out, and now it's better. Okay, so let's add up the first two. So we get oh, and I want to cancel that. So we're going to do 2x1 plus 3x3, and does that equal 5? This is what I wanted to do. Let's find out. So if we divide both sides by 2, we get x1 plus 3 over plus 3x subscript 3 over 2. We get that equaling 5 over 2. So now we can move this over to the other side. Now we get 3x3 over 2 equals 5 over 2 minus x1. So now we can multiply both sides by 2. Okay. And on this side, they cancel each other out. So we get 3x subscript 3 equals, so here it cancels out, so equals 5 minus x 1 over 2. Okay, so now we can move this back over and we can have it equal 5 again. Wait, I'm confused. Oh, I guess it's just saying that you can easily infer from the first and the second and the third that x equals 1, because we can see 3 instances of a quantity added together equals 3. So obviously that quantity would be 1, because 1 plus 1 plus 1 equals 3. So that's like an obvious thing we can see because it equaling 3. And then the last one we can see two instances of a quantity added together equals 2. So that's another one that it equals 1. So from the first and third equation, it's pretty it's obvious that x equals 1 in those equations. So from adding the first and second equation together, we get an equation that equals 5. And x equals 1 again. So we know that x, yeah, we know that the only possible and unique solution. How do we know there's not another solution though? Oh, and why did my share time out? Okay, so now it's back. I'm sorry, I don't know how long that was going for. But anyways, that's kind of a fail. I'm more confused after doing that. But the cool thing I can do, and let me actually undo all this erasing here. Now that I've got it screen sharing, take a look at this. I can take my own handwriting now, and I can go over to ChatGPT, and I can paste in my own handwriting. Isn't that cool? What a world we live in. And let's see what it has to say about it. So it looks like you're working through the system of equations from example 2.6. Isn't that cool? And it doesn't even say 2.6 anyway. Let me help clarify and walk through what's happening based on your work. Isn't that cool? Like, isn't that awesome? So the third equation is redundant because it can be derived from the first two equations. Oh, but did it get the wrong one? Yeah, I was working through 2.5. Okay. That's why I was confused, I think. Sorry, I was trying to work through 2.5. I think that's why 2.5. I think that's why I was getting confused. Yeah. Okay, so the three equations do not contradict each other. They intersect at one specific point. There's a unique solution because the system perfectly aligns without redundancy or contradictions. Okay, and we can do that by solving for x1, x2, and x3. So equation 1 we can rearrange. There we go. Look at that. Isn't that cool? Let me try that. So oh, and it stopped sharing again. I'm not sure why it does that. That's kind of annoying, but it's not the end of the world. It's just slow and annoying. Oop. Oops, still slow and annoying. Huh. Now it's just straight up not working. Okay, there we go. We're back. So, yeah, let me try that. So what I want to try to figure out is why can't it be anything else? Oh, and my mouse got captured, so I just do a Control Tab, and now it's free. So let me start by writing out the equations. Equals 3. Oops, and that's a minus. Equals, and that equals 2. And then the third one is x subscript 2 plus x subscript 3 equals 2. So we have equation 1 here, equation 2 there, and equation 3 there. So let's get, let's start with equation 1, and let's rearrange it so that we have the value of x1 and what that equals. So that equals 3 minus x2 minus x3. Okay, and now we can plug that into to another one. Yeah, so let's plug that into the second one. So the second one, now we know what x1 is. X1 is 3 minus x2 minus x3. We know that minus, and we could drop the sign. Minus x2 plus 2x3. We know all of this equals 3. And we also know from the third equation, we know what x2 plus x3 equals. So so let's move an x2, which we have here, and an x3 over to the other side. So now we have so we're gonna do 2 plus x2, because we have that here, so we can if you think of a number line, we start at 0. We're gonna move 1 this way, so one quantity that way, so the quantity is going to be x subscript 2. But then we're going to move one quantity back, so it's actually the other way. So we're moving one quantity this way. We'll say that this quantity x2 for now is 1, and then we're moving one quantity back, so we didn't make any changes to where it is on the number line. So now we've got plus x2 plus x3, and we've got that equaling. Oh, and it looks like unfortunately it stopped sharing, which is really annoying. I don't know why it does that, but that is a game-breaking thing. If it's gonna just stop sharing randomly or for a limited amount of time, then it's not useful. So we took care of these values here, so they're now gone. And on this side now we have 3 minus 2 plus 2x subscript 3. But we know what this is. It's given by the equation there, so we know that it's a value of 2. So this is actually a 2 right here. So now we have 2 plus 2 on this side because we know what that is. So and then that equals 4. We know that. So then we have 3 minus x2 plus 2x3 equals 4. So can we do this again? What if we move the let's move this to the other side. So now we've got 4 plus x2 minus 2x3 equals 3. Because I'm trying to get to this. Oh, but you know what? So you know what? I'm already there because we have let me undo here a bunch of them. So look at this. Does this look familiar? So we've got we know that we know that x1 equals 3 minus but this part here should look familiar. It's the same thing up here. I'm confused now. But we can't plug that in because we don't know what. Well, we do know what x1 equals. X1 equals this. So let's plug that in. So oh, you know what? Actually, we saw this. Oh no, but it's not the same. It's not the same as what's up there. Huh. Well, you know what? We have the value of x2. So x2 would be 3 minus 4 plus 2x3 equals x2. So that'd be negative 1 plus 2x3 equals x2. Oh, and it stopped sharing again. So unfortunately, this isn't going to be a acceptable solution because it looks like it only shares for about a minute or so, and then it just randomly stops sharing with without any sort of notification or anything like that. So that's not going to be a good solution. We'll have to figure out a better one. And then it has a lot of difficulty starting the share as well. It just takes a while to start the share, and then it stops it automatically without any sort of indicator that it has stopped. All right. Well, you know what? I'm usually only good for like an hour when it comes to doing complicated things on my YouTube channel. So I think I'm gonna have to end it here. I'm doing 2 hours. Yep, and it failed to screen share. So so yeah, it's not gonna be easy. I haven't done serious math probably since high school, so it's a challenge for sure. But I'll do my best. This is the easiest time in human history, I would say, to learn math. We saw how helpful ChatGPT was. So so I'll give it another shot. I'll try to be more consistent with it, but I do have to find the right balance between doing something like this and doing other things in my life. And doing something like this might be pretty low on the list of priorities. But yeah, that's it. Hopefully at some point I'll get my tablet mirroring working better, so people can see me working out things that way, the equations by hand, and we can feed my attempts into ChatGPT and figure out where I went wrong. But for now, that's going to be the end of this video, so stay tuned for the next one, where we'll go over section 2.2 on matrices. So let me advance my bookmark. Look for blue highlights because we don't want any blue highlights. Look for bookmarks and advance the bookmark. All right, and that's it for this video. Thanks for watching. See you in the next one.